material that are on the surface. So the first step is to remove nitrogen. These mean low argon and krypton content in nitrogen. Remove nitrogen with high purity water. Once the sphere is filled with water, we replace water with scintillator. So you can see here, sure, water is heavier than nitrogen. This means that we put water from the bottom. But when we have to put the scintillator, we have to fill from the top, because the scintillator is lighter than water. So we put scintillator and we spill water from the bottom. And this is the picture once the detector was completely filled. It was 1 year ago. Okay. From this data, we began to take data. So I want to show you what data looks like. For example, the first thing was to count how many uranium and thorium we have. Our specification was, do you remember, 10 to minus 16 grams per gram. Okay? It's possible to count how many thorium you have, looking for, this is the chain I was speaking before. I mean, you have thorium, it decay alpha of radium 228, it decay beta on actinium 28, and so on, until it reaches a stable nuclide that in this case is lead 2O6, 2O8. Okay. So, in this chain, you have this very fast coincidence. When you reach the bismuth to 12, bismuth undergo bit decay, and within 432 nanoseconds, the polonium 212 that is created by the bismuth decay alpha. So, in a very fast window in time, you can't, if you see an alpha that, or you can say a beta followed by an alpha in this time, you can infer the alpha of this nuclide. So you can count how many polonium 212 you have. And in the case you have a secular equilibrium, I mean there is no broken chain because it's a different motivation. If you are able to count how many polonium 212 you have, you can say how many thorium 232 you have. Okay? So thanks to this fast coincidence, you can infer the amount of thorium, and we found out that the amount of thorium was 6.8 plus or minus 1.5, 10 to minus 18 compared to this one. Not only we were able to reach such a low content, but you can say 10, 15 times lower than predicted. Okay? And this means that if you count at the same time, the same way I made before, with this amount you have 0.25 grams per day. You remember we expect something on the order of 30 ergs per day. What do you mean?
That the background is 30 times smaller.
This is the specification. I said before that if I wanted to have a signal to noise ratio on the order of 1, I have to reach 10 to minus 16. And we found out that it was lower than
But this one was a requirement.
Yes, this
is a requirement.
The specification.
So, and then you realize that it is 30 times smaller.
Yes.
But perhaps this could be a bad sign. Maybe the efficiency is smaller.
Or I can say maybe, you know, in case.
Okay.
This is why until 1 year ago we said, okay, our goal is the beryllium-7 measurements. When I say beryllium-7, I meaning the neutrino coming from beryllium-7. Now that we have found that the amount of contamination is better than the view, we say that, okay, beryllium-7 is our main goal, but there are other goals. the one I mentioned before. We want to measure CNO neutrino, PP neutrino maybe, PAP and so on. Okay, you can see here, this is the events versus the radius. You remember when I said the vessel is 8.5 meters in diameter. This means 4.25. Okay, and I said that if you count events in the outer part of the inner vessel, you are sure that this one comes from outside. So what I'm saying is that here these events are not events that took place, that it's for sure are not events due to the neutrino. Maybe there is some events due to the neutrino, but the bump is due to the gammas from the photomultiplier. So if I cut to the first 3 meters, I eliminate all these counts, okay? In order to maximize, as I said before, the signal to noise ratio. This is the same pitch if you want. This is, you see, this is the very center of the detector, minus 4.25 plus 4.25, the same thing. This candidate took place near the vessel. This means that actually is a thorium that is on the vessel itself. Gammas from outside, but also beta and alpha that are inside the balloon. Okay? So there are also some candidate for sure in the scintillator itself. When I refer to this number, I mean once we have eliminated all the elements we know that are background. Okay? The same thing was made for uranium. This is the chain of uranium. We see at the same level. Instead of bismuth to 12, we have bismuth to 214. Is undergo to beta and alpha decay with this time. So we count for the polonium 214. And in the case of secular equilibrium, we can infer how many uranium we have. And it turned out that the number was this one. 5 times better than the specification. Okay? And this is accounted only for 2 count, about 2 count per days in 100 ton, compared to the 30-40 we expect. Okay? So uranium and thorium is not a problem. What is a problem is polonium-210. In this chain, at a certain level, after this one, we have polonium-210. Normally polonium is created by bismuth-210 and is created by lead-210. This one is very troublesome because if you have lead-210, lead-210 has an half-life of 22 years. This means that if you have lead inside, lead-210 inside the scintillator, you have always polonium-210. This is created by this one. It turned out that we see a lot of events due to this nucleus, about 6,000 events per day in 100 tons, 6,000 compared to 30, okay, 6,000. And it decay with its half-life that is on the order of 200 days. So, when we started, we had 6,000, and now, roughly 1 year after the first events, we have something on the order of 1,000, 1,000 and a half. Okay? So it's not in equilibrium, fortunately, with lead. This means that we have seen the way that it come out. But as you can expect, how I can hope to find out neutrino on the order of some tens of events per day when I have a background that is on the order of thousands of events. We will say that we are able to separate alphas from betas. When I said before, I come back, how many minutes?
1 minute. 1 minute.
1 minute. So,
How many?
Không, không.